In the YouTube video titled Lecture 8, Advanced Encryption Standard, AES, by Christof Paar, Professor Paar commences his lecture by contextualizing the historical genesis of AES. He posits that cryptography is a relatively young discipline, highlighting the rapid evolution of cryptographic standards. As a case in point, he cites the Data Encryption Standard, DES, which was widely adopted in the 1970s but became susceptible to attacks by the late 1990s due to its inadequate 56-bit key length. This vulnerability prompted the United States government to initiate a search for a more robust encryption algorithm, leading to the development of the Advanced Encryption Standard, AES. Professor Paar meticulously outlines the AES selection process, a testament to the rigorous standards and open competition within the field. He elucidates that NIST solicited proposals from cryptographers worldwide, ultimately receiving 15 submissions. These submissions were meticulously scrutinized and narrowed down to 5 finalists. After 2 years of intensive analysis and evaluation, the Rijndael algorithm, developed by 2 Belgian cryptographers, emerged as the victor. Professor Paar emphasizes the openness of the AES selection process, underscoring its transparency and the global collaboration of cryptographers in scrutinizing and evaluating potential candidates. Professor Paar subsequently shifts his attention to the structure of the AES algorithm, highlighting its key distinctions from DES. He introduces the principle of key whitening, a crucial aspect of AES that strengthens the cipher by applying a subkey to the plaintext at the beginning and conclusion of the encryption process. AES incorporates a 128-bit block size, significantly amplifying its key space compared to DES and enhancing the overall security of the cipher. The heart of the AES algorithm lies in its multi-round structure, where each round is characterized by a sequence of 4 distinct layers: byte substitution, shift rows, mix columns, and key addition. Professor Paar delves into the core principles of diffusion and confusion, fundamental tenets of modern block ciphers. He explains that the byte substitution layer in AES is primarily responsible for introducing confusion, effectively obfuscating the relationship between plaintext and ciphertext. He proceeds to illustrate how this layer is implemented through a series of operations within the Galois field GF2. The byte substitution layer entails calculating the inverse of the input byte in GF2 and subsequently applying a fixed affine transformation. Professor Paar underscores the pivotal role of Galois fields in AES, underscoring its integral nature in the cipher's design. He then turns his attention to the shift row layer, a crucial component of diffusion within AES. This layer rearranges the bytes within the state, ensuring that changes in individual bytes propagate throughout the entire cipher, effectively enhancing the cipher's resistance to attacks. Professor Paar culminates his explanation by delving into the mix column layer, responsible for intricately intermingling the bits within the state. This layer involves matrix multiplication within GF2, playing a critical role in bolstering the diffusion properties of AES. Professor Paar concludes his lecture by emphasizing the paramount significance of AES as the most extensively utilized symmetric algorithm in contemporary cryptographic practices, a testament to its robust security and intricate design. From 0 minutes to 5 minutes of the video, Professor Paar welcomes students to the second lecture on AES, the Advanced Encryption Standard. He briefly summarizes the previous week's lecture, noting its unusual focus solely on mathematics, specifically Galois fields, the importance of which will become apparent during the current session. The professor informs the students that the lecture will cover AES in detail, from its origins to decryption, and he suggests that they should pay close attention to the lecture's dense content. He also humorously suggests that the first 10 minutes, which will be dedicated to a historical overview, can be used for a short nap, although students are still instructed not to speak. From 5 minutes to 10 minutes of the video, Professor Paar provides a historical overview of the Advanced Encryption Standard, AES, selection process, highlighting its significance in contemporary cryptography. He begins by explaining that the National Institute of Standards and Technology, NIST, in 1997, issued a call for a new encryption algorithm to replace the aging and increasingly vulnerable Data Encryption Standard, DES. This call was directly precipitated by the growing susceptibility of DES to cryptanalytic attacks. The professor, surprised that NIST only received 15 submissions, recounts that NIST whittled down the pool of candidates to 5 finalists in 1998. In a dramatic turn of events, the Belgian cipher Rijndael, developed by 2 young cryptographers, was ultimately chosen as the AES in 2000, triumphing over proposals from prominent names like Ron Rivest and IBM. Professor Paar underscores the paramount importance of AES in the field of modern cryptography, asserting that it is now the most widely used symmetric algorithm globally. He then delves into the structural features of AES, noting that it is a block cipher operating on 128-bit blocks and offering 3 distinct key lengths: 128 bits, 192 bits, and 256 bits. The round structure of AES deviates from DES, employing 10 rounds for 128-bit keys, 12 rounds for 192-bit keys, and 14 rounds for 256-bit keys, a design choice rooted in enhancing the cipher's security with longer key lengths. From 10 minutes to 15 minutes of the video, the speaker embarks on a detailed exploration of the structural underpinnings of the Advanced Encryption Standard AES. He posits that a single AES round comprises 4 distinct layers: byte substitution, shift rows, mix columns, and key addition. The speaker then delves into byte substitution, a substitution layer that performs a replacement operation on 8-bit blocks. Illustrating the concept with a concrete example, he clarifies how to interpret the accompanying table, demonstrating the process of mapping a bit string to a polynomial using Galois fields. He then elaborates on the computation of the inverse of a polynomial, emphasizing that this involves multiplying the original element by the inverse element. Further clarifying the definition of the inverse, he explains it as the product of the original element with the inverse element. From 15 minutes to 20 minutes of the video, Professor Paar delves into the crucial concept of diffusion within the context of modern block ciphers. He elucidates this principle using a practical illustration. Envision an input consisting of 128 bits, all set to 0. Upon encryption with a specific key, the resulting output yields a ciphertext, denoted as Y1. Now, if a single bit within the input is flipped, the desired outcome is that the new output, Y2, appears entirely dissimilar to Y1. This embodies the essence of diffusion, where a solitary alteration propagates throughout the output, effectively thwarting any potential exploitation of correlations by an adversary. Professor Paar subsequently introduces the notion of key whitening, wherein a subkey is XOR'd with the plaintext at both the commencement and conclusion of the encryption process. This widely adopted practice in contemporary ciphers contributes significantly to bolstering their overall security. He concludes this segment by briefly touching upon the concept of key widening, emphasizing its vital role in fortifying the cipher's robustness against various attacks. From 20 minutes to 25 minutes of the video, the speaker elucidates the structure of AES and its divergence from DES. In AES, each round involves 4 distinct transformations: byte substitution, shift rows, mix columns, and key addition. Unlike DES, which encrypts only half of the data path per round, AES encrypts the entire 128-bit data path in a single round. The speaker then proceeds to elaborate on the concept of diffusion, a fundamental principle in modern block ciphers. Diffusion ensures that a solitary bit alteration at the input results in a cascading effect, modifying numerous output bits. This diffusion property is realized through the mix columns layer, which exerts influence on 32 output bits, effectively impacting a quarter of the entire data path. The speaker then commences an explanation of the byte substitution layer, conceptually a straightforward transformation that bears resemblance to the SPOXes employed in DES. From 25 minutes to 30 minutes of the video, the speaker delves into the intricate structure of the Advanced Encryption Standard AES, specifically elucidating the byte substitution layer. They articulate that AES operates on a byte-oriented basis, meaning it manipulates data in units of 8 bits. The speaker underscores that all 16 SPOXes within AES exhibit uniformity, in contrast to DES, which employed 8 distinct SPOXes. To illustrate this substitution process, the speaker presents a concrete example. Given the input hexadecimal value, C2, the corresponding output 25 is located in the SPOX table. The speaker elaborates on the byte substitution process, highlighting its reliance on a transformation of the input byte into a polynomial within the Galois field GF2. The inverse of this polynomial is then computed, followed by the application of a specific fine mapping transformation to yield the output byte. A practical example is provided. The input C2 is converted to the polynomial x plus 1. Upon computing the polynomial's inverse, which is x plus x superscript 2 plus 1, the fine mapping transformation is applied, resulting in the final output byte 00100101 in binary representation or 25 in hexadecimal. The speaker then introduces the concept of diffusion within the context of AES. They clarify that the objective of diffusion is to ensure that a change in a solitary input bit manifests as alterations in multiple output bits, thereby rendering the correlation between input and output less predictable. The speaker emphasizes the pivotal role of the mixed column layer in achieving robust diffusion, asserting that a single bit flip in the input can propagate to up to 32 output bits. The speaker concludes this segment by stressing that the byte substitution layer, the shift row layer, and the mixed column layer collectively contribute to ensuring both confusion and diffusion in AES, making it a cipher renowned for its high level of security. From 30 minutes to 35 minutes of the video, Professor Paar delves into the intricate mechanics of the byte substitution layer within the Advanced Encryption Standard AES algorithm. He draws a parallel between this layer and the S-box layer employed in the Data Encryption Standard, DES, emphasizing their structural similarities. However, a key point of divergence emerges. Unlike the 8 distinct tables found in DES, all 16 S-boxes in AES are identical, exhibiting a remarkable uniformity in their functionality. To elucidate the process of navigating the S-box table, Professor Paar presents an illustrative example using the hexadecimal input value C2. He meticulously explains that the initial hexadecimal digit, C, serves as the row identifier, while the second digit, 2, represents the column. Consulting the S-box table reveals that C2 maps to the output value 25 in hexadecimal notation. Professor Paar then ventures into the profound mathematical underpinnings of the S-box construction. He posits that an input byte can be conceptualized as an element within the Galois field GF, 2 to the power of 8, effectively representing a polynomial. In his illustrative example, the input value C2 translates to the polynomial x to the power of 7 plus x to the power of 6 plus 1. This polynomial undergoes an inversion operation, culminating in the polynomial x to the power of 5 plus x squared plus 1, which corresponds to the hexadecimal output value of 25. Professor Paar clarifies that this inversion process entails a series of mathematical operations, including multiplication and modulo reduction, utilizing the irreducible polynomial x to the power of 8 plus x to the power of 4 plus x cubed plus x plus 1. This intricate sequence of operations is systematically applied to each of the 256 possible input values, generating the exhaustive S-box table. He concludes this section by highlighting the sophisticated mathematical underpinnings of the S-box construction in AES, emphasizing its stark contrast to the S-box implementation employed in DES. From 35 minutes to 40 minutes of the video, Professor Paar delves into the intricacies of the byte substitution layer within the Advanced Encryption Standard, AES. He commences by emphasizing that AES operates on a byte level, with each byte comprising 8 bits, a stark departure from the bit-oriented DES algorithm. This layer involves a systematic transformation of each byte of the input data, utilizing a specific lookup table to replace it with a distinct value. Professor Paar provides a concrete example, using the hexadecimal value C2 as input, which translates to the binary representation 1100. Using the S-box lookup table, he determines the corresponding output for 1100, which is 0101, or 5 in hexadecimal. This process is repeated 16 times in parallel, employing 16 independent S-boxes. Essentially, this layer affects a substitution of the input byte with a novel output byte. Professor Paar underscores the crucial role of Galois fields in this transformation, elucidating that the input byte is conceptually treated as a polynomial within the Galois field GF2-8. In the given example, this translates to the polynomial x to the power of 7 plus x to the power of 6 plus x. He further emphasizes that the 16 S-boxes operate concurrently, indicating that the 16 substitution operations are performed simultaneously. This parallel execution significantly enhances the efficiency of the byte substitution layer. From 40 minutes to 45 minutes of the video, the speaker transitions from a high-level overview of the AES structure to a more granular examination of individual layers. He commences by elucidating the shift-row layer, a seemingly complex operation that is, in fact, a straightforward byte permutation. The speaker visually illustrates this process by representing the input as a 4x4 matrix and demonstrating how each row is cyclically shifted to the left by a specific number of positions, with the second row shifted by 1 position, the third row by 2 positions, and the fourth row by 3 positions. This systematic byte transposition, the speaker emphasizes, is instrumental in achieving the vital cryptographic principle of diffusion. Moving forward, the speaker delves into the mixed column layer, characterizing it as a comparatively simple operation involving matrix multiplication. He uses the first mixed column box as a concrete example, meticulously demonstrating the calculation of the output C0 using the formula C0 equals O2 asterisk B0 plus O3 asterisk B5 plus O1 asterisk B10 plus O1 asterisk B15. In this formula, the constants O2, O3, and O1 represent elements of the fixed matrix, while B0, B5, B10, and B15 denote the corresponding input bytes. The speaker underscores that this matrix multiplication occurs on an 8-bit level, highlighting the byte-oriented nature of the AES algorithm. The mixed column layer, the speaker asserts, serves a crucial function in ensuring that any input changes, even a single-bit flip, are propagated across all 4 output bytes, thereby achieving robust diffusion. From 45 minutes to 50 minutes of the video, the speaker delves into the concept of diffusion as it pertains to AES. He elaborates on the principle that a single-bit modification in the plaintext should instigate substantial alterations in the ciphertext, thereby rendering it intractable for adversaries to exploit any discernible correlations. To elucidate this notion, he posits a scenario involving a plaintext consisting of 128 bits, all initialized to 0. Upon encryption, the resulting ciphertext exhibits a seemingly random character. He then introduces a perturbation by inverting a single bit within the plaintext, generating a modified plaintext. The desired outcome is a ciphertext that demonstrably diverges significantly from the original, thus substantiating a robust diffusion effect. The speaker pinpoints the mixed column layer as a pivotal component in achieving this objective. He describes it as a matrix multiplication operation, where a predefined matrix is multiplied by 4 bytes, B0, B5, B10, B15, to yield the corresponding ciphertext bytes, C0, C1, C2, C3. Each plaintext byte undergoes a transformation influenced by this multiplicative process, resulting in a cascading effect where a solitary bit alteration in the plaintext propagates to alter all 4 ciphertext bytes. This diffusion characteristic is instrumental in bolstering the security of the encryption process. The speaker highlights the significance of this mechanism, asserting that it ensures even a minor plaintext modification triggers a substantial shift, affecting 32 bits, or a quarter of the overall data path, in the ciphertext. This underscores the robust diffusion property inherent to AES. The speaker concludes this segment by reiterating the pivotal role of the mixed column layer in AES, emphasizing that it serves as a critical element in achieving a pronounced diffusion effect, thereby rendering the encryption algorithm more resistant to cryptanalytic attacks. From 50 minutes to 55 minutes of the video, the speaker delves into the key whitening process intrinsic to the Advanced Encryption Standard AES, a cryptographic principle notably absent in its predecessor, the Data Encryption Standard DES. AES incorporates a key-dependent round structure, wherein the number of rounds employed directly corresponds to the key length, thereby bolstering security. This mechanism manifests as the addition of a subkey to the plaintext at the commencement of encryption and, once again, at the final stage of the procedure, a process aptly termed key whitening. The speaker emphasizes the significance of this key-dependent round structure, highlighting that 10 rounds are executed for a 128-bit key, 12 rounds for a 192-bit key, and 14 rounds for a 256-bit key. The speaker underscores the high level of confidence the National Security Agency, NSA, places in AES's robustness by noting its adoption for the protection of classified data. From 55 minutes to 60 minutes of the video, the speaker delves into the table from the textbook, specifically Figure 4.3, which represents the S-box transformation in AES. He elucidates the table structure and provides an illustrative example of its use. The input value AI, denoted as C2 in hexadecimal notation, is analyzed. The speaker underscores that the first hexadecimal digit corresponds to the X coordinate and the second digit to the Y coordinate. Therefore, with X as C, the C row is selected, and with Y as 2, the output is located at the intersection of the C row and the 2 column. This process reveals the output value 25, implying that BI is equivalent to the S-box transformation of AI. The speaker emphasizes that this table lookup procedure bears a strong resemblance to the method employed in DES for reading S-box tables. He then highlights a key distinction between AES and DES. All 16 S-boxes in AES are identical, whereas each of the 8 S-boxes in DES is unique. From 60 minutes to 65 minutes of the video, the speaker transitions from a high-level overview of the Advanced Encryption Standard, AES, to a detailed examination of the individual layers within each round of the algorithm. He first elucidates the shift row layer, demonstrating how this layer acts as a byte permutation to ensure diffusion, a core principle in cryptographic design. This permutation is realized by treating the 128-bit data block, the state, as a 4x4 matrix, with each row undergoing a systematic circular shift. The first row remains untouched, while the second, third, and fourth rows are shifted 1, 2, and 3 positions to the left, respectively. The speaker then focuses on the mixed column layer, where a more complex operation is performed to further enhance diffusion. This layer utilizes a matrix multiplication with a fixed matrix, where each column, comprising 4 bytes, of the state undergoes this transformation. The speaker emphasizes the importance of this step for avalanche effect, the phenomenon where a small change in the input leads to a substantial alteration in the output, thereby obfuscating any potential correlation between plaintext and ciphertext. He provides a concrete illustration showing how the first input byte, B0, is multiplied by a matrix constant, O2, and subsequently added to the products of the other matrix constants, O3, O1, O1, and their respective input bytes, B5, B10, B15. This results in a single output byte. The speaker highlights that any change in a single input byte within the mixed column layer results in changes to all 4 output bytes, leading to a significant diffusion of changes across the entire data path. In essence, the mixed column layer serves as a critical element in ensuring avalanche effect in AES, amplifying the impact of small changes in the input and rendering the ciphertext highly unpredictable. This intricate interplay of permutations and matrix multiplications, meticulously crafted within each round, strengthens the security of AES, making it a formidable cipher against various cryptographic attacks. From 65 minutes to 70 minutes of the video, the speaker transitions to elucidating the shift row layer, emphasizing its role as a byte permutation within the AES algorithm. He demonstrates this operation using a visual representation of the state, which is depicted as a 4x4 matrix comprised of bytes. The shift row layer operates by maintaining the byte structure while systematically reordering the bytes. For instance, the second row is cyclically shifted 1 position to the left, resulting in the first byte, B1, being moved to the final position, the second byte, B2, becoming the first byte, and so forth. This cyclical shifting ensures that data propagates across the state, contributing to the diffusion property of AES. The speaker clarifies that the last row is shifted 3 positions to the left, adhering to a cyclical pattern where bytes shifted beyond the final position wrap around to the initial position. He emphasizes the systematic nature of this operation, underscoring its crucial contribution to the diffusion property of AES, which mandates that changes in 1 byte should influence multiple other bytes within the algorithm. From 70 minutes to 75 minutes of the video, Professor Paar delves into the concept of diffusion within AES, illuminating its pivotal role in the design of contemporary block ciphers. He commences by defining diffusion as the property wherein a modification of a single bit in the input results in a substantial alteration of the output, ideally impacting a significant number of bits. To illustrate this principle, he presents a scenario involving the flipping of a single bit within a 128-bit input. The ramifications of this alteration become evident throughout the AES rounds, with the change potentially cascading to multiple bytes. Paar underscores the mixed column operation within AES as a catalyst for achieving robust diffusion, emphasizing that a solitary bit modification in a byte input can instigate changes across all 4 output bytes during a single round. This results in a scenario where a substantial portion, approximately 1/4, of the complete 128-bit data path is influenced within a single round. Professor Paar concludes by emphasizing the critical function of the mixed column operation in AES, which effectively disperses alterations across multiple bytes within a single round, thus achieving a high degree of diffusion. From 75 minutes to 80 minutes of the video, the speaker delves into the intricate workings of the Advanced Encryption Standard, AES, meticulously elucidating the functionality of its constituent layers. Commencing with byte substitution, a process analogous to that employed in the Data Encryption Standard, DES, the speaker explains how this layer substitutes an 8-bit sequence with a predetermined value. However, a crucial distinction arises in the SPOCs utilized by AES, which is meticulously engineered through mathematical principles. This SPOCs leverages the concept of Galois fields, previously explored in the preceding week's lecture, and entails the following sequence of operations. 1. The input byte is interpreted as an element within the finite field GF. 2. A mathematical structure encompassing 256 distinct elements. 2. A computation of the multiplicative inverse of this element is performed within GF. 2. 3. The inverse element is subjected to multiplication with a fixed matrix, an integral component of the AES standard, employing modular arithmetic, modulo 2, to constrain the result within the designated field. 4. A constant vector is then added to the product obtained in the preceding step. 5. The outcome of this series of operations constitutes the SPOCs' output. Next, the speaker explores the shift row layer, a straightforward permutation of bytes within the state, a 4x4 matrix that serves as a representation of the 128 bits constituting the data path. The speaker then underscores the paramount importance of the mixed column layer, which involves a matrix multiplication operation utilizing a fixed matrix. This multiplication is performed within GF, 2, and plays a critical role in achieving diffusion, a fundamental cryptographic principle. Diffusion ensures that any alteration in the input data leads to changes in multiple output bytes, effectively obscuring the relationship between the input and output and enhancing the cipher's resilience against cryptanalysis. This process constitutes a cornerstone of the AES algorithm's security. From 80 minutes to 85 minutes of the video, Professor Paar delves into the shift row layer of the Advanced Encryption Standard, AES, algorithm, highlighting its role as a byte permutation. He elucidates that this layer serves to permute the bytes within the data path, effectively rearranging their positions. Utilizing a 4x4 matrix representation of the data path, Professor Paar illustrates this process, demonstrating how each row is shifted cyclically to the left. The first row remains unchanged, the second row undergoes a 1-position shift, the third row a 2-position shift, and the final row a 3-position shift. This systematic rearrangement aims to achieve a crucial cryptographic principle: diffusion. Professor Paar then transitions to the mixed column layer, an essential matrix multiplication operation that further enhances diffusion within the AES algorithm. He emphasizes that this layer ensures that a single bit change in the input will invariably affect all 4 output bytes. Professor Paar presents a visual representation of the constant matrix used for this operation, noting that the multiplication is performed within the Galois field GF, 2 to the power of 8. He highlights that this multiplication involves a module 2 reduction step, ensuring that the output remains a byte. Professor Paar proceeds with a concrete illustration of the mixed column operation, outlining the steps. 1. The input consists of 4 bytes, B0, B5, B10, and B15. 2. Matrix multiplication is applied to these bytes as taught in linear algebra. For example, the calculation for the first output byte, C0, is C0 equals O2 asterisk B0 plus O3 asterisk B5 plus O1 asterisk B10 plus O1 asterisk B15. 3. This matrix multiplication is iterated for all 4 output bytes. 4. Each element within the matrix is represented as a byte in hexadecimal notation, leading to the utilization of standard 8-bit operations for the multiplication. In conclusion, Professor Paar effectively conveys the significance of the mixed column operation. Through this systematic byte permutation, any single bit change in the input will cascade into a substantial modification of the output, affecting approximately 32 bits. This outcome demonstrates the powerful diffusion characteristic of the AES algorithm. From 85 minutes to 90 minutes of the video, the speaker delves into the shift row layer of AES, elucidating its function as a byte permutation. The speaker underscores the simplicity of this layer, highlighting that it merely involves the systematic rearrangement of bytes. Employing a 4x4 matrix for illustrative purposes, the speaker visually demonstrates the shifting of each row to the left by a predetermined number of positions. The second row, for instance, is shifted by 1 position, the third by 2, and the fourth by 3, creating a cyclical pattern. This visual representation serves to effectively convey the byte permutation within the matrix. Moreover, the speaker emphasizes that each of the 4 groups of 4 bytes is interconnected with a distinct mixed column box, thereby ensuring a pervasive spread of influence across the data path, thus enhancing diffusion for improved security. From 90 minutes to 93 minutes of the video, the speaker delves into the intricate structure of the Advanced Encryption Standard, AES, elaborating on its 4 distinct layers: byte substitution, shift rows, mixed columns, and key addition. He contrasts AES's comprehensive encryption of the entire 128-bit data path within a single round with the more limited encryption of DES, which encrypts only half of the data path per round. Transitioning to the shift rows layer, the speaker clarifies its fundamental nature as a byte permutation, involving the methodical rearrangement of bytes within a 4x4 matrix. This is visually demonstrated through the systematic shifting of each row to the left by a specific number of positions, the second row by 1 position, the third row by 2 positions, and the fourth row by 3 positions. The speaker then addresses the mixed columns layer, acknowledging its greater complexity and its reliance on matrix multiplication with a fixed matrix. This multiplication is executed using modulo 2 operations, indicating that all calculations are modulo 2, and a constant vector is incorporated. Finally, a bitwise XOR operation generates the final SPOX output.